Hi everyone! In this video we are going to take a look at some similar figures, both two-dimensional and three-dimensional, and investigate what the relationship is among their perimeters, the areas, and the volumes of these similar figures. Before we start the lesson today, I just want you to think about something. If you have a square, just a simple square, and you change the dimensions of that square, so let's say you triple it, so it's getting, each side of the square is getting 3 times as big. What happens to the area? Does the area get 3 times as big, or does something else happen? Another scenario I want you to think about is to picture something three-dimensional. Let's say like a cylinder. So you take a cylinder and you take the radius of that cylinder and you make it 3 times as big. What happens to the surface area of the cylinder? Is it also 3 times as big? Think about the volume of that cylinder. If the radius got 3 times as big than the first one, is the new cylinder have 3 times the volume or something different? That's what we're going to explore today. We're going to start today by looking at two-dimensional figures, and then we're going to move into three-dimensional figures. With two-dimensional figures, we're going to look at the perimeters and the areas of two similar shapes and see if we can find some patterns about how their ratios compare. Okay, so for these first two triangles, let's go ahead and find the perimeter and area. We are going to need to find that third side. We can use the Pythagorean theorem, or we can just, if we can remember our Pythagorean triples, 3, 4, 5 is one of our common right triangles. So if this is 5, then the perimeter would just be 12. For the other triangle, it's just a double of that triple. So instead of 3, 4, 5, it's 6, 8, 10. So the perimeter of that one would be 24. And then for the area, we would do 1/2 base times height. So 1/2 times 3 times 4. 1/2 of 12 would be 6. And for the one on the right, again, 1/2 base times height, or 1/2 6 times 8. So 1/2 of 48, or 24. Okay, so the ratio of the sides, we could pick any of the corresponding sides, and we can see it's either 3 to 6, or 4 to 8, or 5 to 10, but that would all reduce to 1 to 2. And then the ratio of the perimeters, we would do 12 to 24, which again reduces to 1 to 2. And then the ratio of the areas, we're looking at 6 to 24, which reduces to 1 to 4. I'll just put that here so you can see how we started that and then we reduced it. And this one was 12 to 24. Okay, let's do it again for these rectangles. This time we are given the 2 dimensions of that small one, but we don't have both dimensions for the larger one. But we know they're similar, so we can figure it out. So we know that those other two sides are in a ratio of 15 to 6. And so we can solve for the length, which would be from x to 16. We can reduce on the left, and if we divide everything by 3, that just makes our work a little bit easier. And then I can notice that I multiplied by 8 to get to here. So if I multiply by 8, I'm going to get that x is 40. So that's the length of this rectangle. So the perimeter would be 2 lengths and 2 widths. So perimeter would be 40 plus 40 plus 15 plus 15. So that's 80 plus 30, so we have 110. And the other perimeter, we would have 2 16s, that's 32, plus 2 6s, that's 12, so 32 plus 12, that's 44. And then for the area, it's just length times width, so 40 times 15, or 4 times 15 would be 60, so that's 600. And the other one is 16 times 6. Let's see, 6 times 10 is 60, 6 times 6 is 36, so that's 96. All right, so the ratio of our sides, we have 15 to 6. Of course, that reduces 5 to 2. I'm going to just write it like that. And the ratio of our perimeters is 110 to 44. What do you think we can divide both of those by? And we can divide by 11, and that gives us 10 to 4. Oh, we can reduce again, and we get 5 to 2. Okay, and then the ratio of areas will be 600 to 96. And let's see, what can we divide both of those by? I know I can divide 96 by 12. Oh, and 12 goes into 602. So 12 goes into 650 times. So that gives me 50 to 8. And I can divide by 2. And now I get 25 to 4. Hopefully you're starting to notice some patterns here. We'll come back and look at that in a minute. Let's do our next one. All right, so for the hexagons, these are just regular hexagons, and they're similar. So the perimeter would be 4 times 6, which is 24 for the first one, and the perimeter for the second one is 12 times 6, which is 72. And for the area, this one's going to take a little more work. We're going to need to do the formula of 1/2 AP. And remember, I'm going to draw it in on the big one first. The apothem looks like this. And if we think about this triangle that gets formed right here, this is an equilateral triangle. That's true in hexagons only. And the reason for that, if you remember, is every angle in a regular hexagon is 120 degrees. So when you draw in this triangle, I'm just going to sketch it over here. This is now a 60-degree angle. This is a 60-degree angle, which means the top is also 60 degrees. So now when I draw that apothem in, we have a 30, 60, 90 right triangle, which that's what makes these a little bit easier when you're dealing with hexagons. So if this whole original bottom here was 12, then when I draw the apothem in, this has turned into 6. And the 30, 60, 90 rule tells us that if that is 6, then the long side is 12, and this apothem here will be 6 radical 3. So that's going to help us to find the area of our hexagon, because we have to do 1/2 times A times P. Let's also do the apothem in the little one. I know it's really small, but if we think about that triangle that will get formed inside there, and here's the apothem. If this is 2 and this length here is double that, which is 4, then my apothem is going to be 2 radical 3. Okay, so back to our formula for area. I have to do 1/2 AP. So for the little guy, it's 1/2 times 2 radical 3 times the perimeter, which is 24. So let's do half of 24. That's 12. 12 times 2, that's 24 radical 3. And then for the big one, 1/2 times the apothem, which is 6 radical 3, times the perimeter, which was 72. So half of 72, that's 36. And 36 times 6, that's 216. So 216 radical 3. Okay, ratio of sides. That was 4 to 12, which is 1 to 3. And the perimeters, we have 24 to 72, which is also 1 to 3. And then for our areas, we're doing 24 radical 3 compared to 216 radical 3. So if you think of that as like a fraction, if you had 24 radical 3 over 216 radical 3, I'll just sketch this over here. Basically, you can cancel out the radical 3's, right? They both have that, so that would cancel out if you were reducing it. And then 24 goes into 216 9 times. So my final ratio of areas, if I reduce this, would be 1 to 9. Because I cancel this part out, this goes to 1, this goes to 9. So we're just left with 1 to 9 for the ratio of the areas. Okay, if you have a highlighter handy right now, that would be really great. If you don't, you can just use your pencil or a pen. If you need to go get a highlighter, you can pause the video for a second. And what I want you to do is go with your highlighter and or just circle all the ratios for each of these 3 shapes. So the final ratio that we reduced. So I want you to highlight this one, the ratio of the sides, the ratio of the perimeters, and then the ratio of the areas, and do that for the other 2 shapes as well. So go up and highlight or circle or box in those ratios for the other 2 shapes. And then just take a second and sort of analyze them. What do you notice? What patterns do you see? You should notice something about how the ratio of the sides compares to the ratio of the perimeters, and then how they compare to the ratio of the areas. And we're going to write some conclusions down here. Okay, so if two similar polygons or circles have corresponding lengths, meaning their widths, their heights, their medians, their angle bisectors, their radii, any length that we know that are corresponding in the shapes, if their ratio is from m to n, like in this hexagon case it was 1 to 3, then their perimeters are also in that same ratio of m to n. It doesn't change. The perimeters have the exact same ratio as whatever the sides are, or whatever the heights are, or whatever the medians are. It doesn't change. Okay, if two similar polygons or circles have corresponding sides, widths, heights, medians, angle bisectors, radii, any of that, in the ratio of m to n, or in this hexagon case 1 to 3, then their areas are in the ratio of what? What happens to m and n when we go to the ratio of the areas? And they get squared. So it becomes m squared to n squared. So the ratio gets squared. So quick example, let's just say you have a ratio of sides of 2 to 7. Then the ratio of the perimeters would also be 2 to 7, but the ratio of the areas would be 4 to 49. Okay, so here we have 4 problems we're going to work through. The moons in this picture are similar by a ratio of 2 to 3, so the ratio of their perimeters would also be 2 to 3, and the ratio of their areas would be 4 to 9. You would just square that area. Okay, the areas of the stars. So notice here we're given the areas. The areas of the stars are in a ratio of 25 to 4. We want to find the ratio of the dimensions. So to do that, you would take the square root, because we're going to work backwards. You would take the square root of each of them, and so the ratio would be in 5 to 2. All right, number 3, the area of these arrows are in a ratio of 27 to 40, and we want to find the ratio of their dimensions. So again, we're going to take the square root. This time they're not perfect squares. So we want to take the square root of 27, and then we take the square root of 40. Now we have to simplify just like we would any other kind of ratio or any other radical. So we want to think about what perfect squares go into these. Well, square root of 9 in 27, so we've got radical 9, radical 3, and then inside of 40 we have radical 4. So radical 4, radical 10. So now we get 3 radical 3 and 2 radical 10. All right, number 4, we have 2 similar hexagons, and we know that KL is 20 and RS is 12, and you can see that those are corresponding sides because of their position in the names of the hexagons. And we know that the area of the first one is 190, and we want to find the area of the second one. So let's find the ratio of their sides. The ratio of the sides is 20 to 12, which I can reduce by 2, and I can get 10 to 6. I can reduce by 2 again and get 5 to 3. So this is the ratio of their sides. Well, that means that the ratio of their areas would be this squared, which would be 25 to 9. So this is the ratio that we're going to use to set up a proportion to find the missing area. If we know the ratio of the areas is 25 to 9, and 25 is for the one on the left, remember, that's the hexagon, JKLMNP, and that's the area that we know, that's 190. So we're going to put 190 next to that one, and then we're going to solve for x. So notice I didn't use the ratio of the sides in my proportion, I used the ratio of the areas in my proportion. So once I have this set up, I'm going to just solve my proportion like normal, where I cross multiply. The product of these two, which is 25x, is equal to the product of these two. So 9 times 190. That's 1,710. So I've got 25x equals 1,710. And then we divide by 25. And so x is 68.4. So that's the area of the other hexagon, and that would be in centimeters squared also. Okay, before we move on to three-dimensional figures, we're going to take a look at some ratio of areas when the shapes are not similar. So look at this particular triangle, ABC. So looking at the outside first. And I've drawn in a median. So AC right here, this is a median. That tells us that this length of CD is equal to this length of BC, right? Those are equal because AC is a median. That's what a median is. So we're going to find the area of a couple different triangles here. Let's start with the area of triangle ABC, this one on the left. And I know we don't have any actual measurements here. We're just going to do this sort of generically. You'll see how this is going to work. So the area would be 1/2 base times height. And the base, I'm just going to fill in here BC, that length of the base. And then the height of that triangle is AO. Okay, now the triangle ACD, that's the one on the left, or sorry, on the right. So we're going to do this one next. And same formula, so 1/2 base times height. And the base is CD. And then the height is the same, right? Because this is this obtuse triangle, the altitude is drawn out here. So this AO is the height for both those triangles, for ABC and for AOC, or for ACD. So the height would still be AO. All right, so compare these two, and you notice that they both have the AO. They have the same height. They both have the 1/2. And then how does the BC compare to CD? BC, if you remember over here, is equal to CD because C was a median. So those are the same exact measurements. So the ratio of the area of triangle ABC to the area of triangle ACD would be 1:1. Because they're equal, right? Those areas are equal. All right, now we're going to compare the ratio of triangle ABC to the area of triangle ABD, that bigger triangle, which we haven't even found yet. So let's go ahead and find the area real quick of triangle ABD. So this would be 1/2 base times height. And the base is now from B to D, but the height is still AO. Okay, so we want to write the ratio of ABC, which was that first one. I'm just going to write the area here. 1/2 BC AO. I'm going to compare that to this new one, the triangle ABD, which is 1/2 BD AO. All right, just like a fraction, we can reduce things that are the same. So they both have this, they can get canceled out, and they both have this. So we're left with this as our ratio. How does BC compare to BD? BC is half of BD, no matter what that length is, because C was a median. So this ratio would reduce to just 1/2, or 1:2. Okay, so think about what just happened here. When you take a triangle, and this will happen for any triangle, because we did this without any numbers, it was just generically looking at the letters. If you take any triangle and you draw in a median like this, it's going to divide that triangle. Even though these two triangles here, these two triangles, this one and this one, they're not congruent, they're not similar, but they happen to have the same bases and the same heights because of the way we drew the median in, and so therefore they have congruent areas. So their areas are in the ratio of 1:1. And then each of these, of course, would then be half of the whole area, which should make sense. So, conclusion, a median of a triangle divides the triangle into two triangles with equal areas. I think that's a really cool phenomenon. Again, it's just a thing that happens because of the way that you find the area of a triangle, even though those two triangles are not congruent and they're not similar. Okay, so now we're on to three-dimensional figures. We have two rectangular prisms here that are similar, and we want to find the volume. And the volume formula is just length times width times height for a rectangular prism. So we're just doing 6 times 2 times 1. It doesn't really matter which ones you're putting in for which thing, for length and width and height. You're just going to multiply them all together. So the volume for the first one is 12. For the second one, we're doing 12 times 4 times 2. So 12 times 4 is 48, and 48 times 2 is 96. And then for the surface area, we are finding the area of all of the different faces and then adding them together. So if we start with the front face, the area of that is 2, and then there's 2 of those, that makes 4. Let's move to the top and bottom. So the area of that one is 6 times 2, or 12, and 2 of those makes 24. And then for the left and right side, that's 6 times 1, which is 6, and 2 of those makes 12. So 24 plus 12, that's 36. 36 plus 4, we have a surface area of 40. Okay, on the left, let's do the same thing. So this little front piece is 4 times 2, that's 8. 2 of those make 16. For the top and bottom, we have 12 times 4, that's 48, and 2 of those makes 96. And then the left and right is 12 times 2, which is 24, and 2 of those makes 48. So adding all of this together, that's 160. And let's look at the ratios. So I put length here in brackets because when we're finding this ratio, it could be of the length, it could be of the radii, it could be of an angle bisector. It just depends on what we're given for different shapes. So I just put length to kind of generically cover all of them depending on the shapes that we're given. So the ratio of the length would be 2 to 4, or 1 to 2, or 6 to 12. And all of those are going to reduce to 1 to 2, or 1/2. And then the ratio of our surface areas, that's 40 to 160. So that would reduce to 1 to 4. And then the ratio of the volumes, that's 12 to 96. And 12 goes into 96 8 times, so we get a ratio of 1 to 8. If you have your highlighter handy from the last time, you could go ahead and highlight our 3 main ratios here. So 1 to 2, 1 to 4, and then 1 to 8. Let's move on to the second one. We have 2 cones that are similar here. And to find the volume of the cone, our formula is pi r squared times the height. So for the first one, we have the radius is 15, so 15 squared, that's 225, and then times 36, and then pi. So 225 times 36, that's 8100. So our first volume is 8100 pi. For the second one, we do the same thing. We have 25 squared, that's 625, times 60 pi, and 625 times 60, that's 37,500 pi. So to find surface area of our cone, it's going to take us a little more work because we don't have the lateral height of these cones that we're going to need, and we're going to need to calculate that. And I realize there's probably not enough space that I've given you right here to do that work, so you might want to go grab just a separate sheet of paper or the back of something, just some scrap paper to show your work. And I'm going to do the same. I'm going to take this and we're just going to move over to a blank screen so I can fit all my work and show you what we're doing. Okay, so the surface area formula of a cone is pi RL plus pi r squared. And like I said, we don't have the L, the slant height of our cone yet. We need to find this. So let's do that first. So a squared plus b squared equals c squared. 15 squared plus 36 squared equals c squared. That's 225 plus 1296. That's 1521, and that does happen to be a perfect square, and it's 39 squared. So the square root is 39. So that is the slant height of this one. For the second one, we could do Pythagorean theorem again, but we also could do a proportion. Let's try it that way. Since we know that these are similar, we can make a proportion for the first one that says, or a ratio for the first one that says 15 to 39. And then the second one would be 25 to x. And we can reduce, we can divide these by 3 and get 5 and 13. And I can see here if I multiply by 5, I get 25. And so 13 times 5 will give me 65. So this slant height here is 65. Okay, so now we're ready to find the surface area of each of these. So for the first one, it's pi RL, so pi times 15 times 39 plus pi r squared, which is pi times 225. So 15 times 39, that's 585 pi plus 225 pi, and we get 810 pi. And let's do the second one. So that's going to be pi times the radius, which is 25, times L, which is 65, plus pi r squared, and 25 squared is 625 pi. So that's 1,625 pi plus 625 pi. And when we add that together, we get 2,250 pi. Okay, so now we just need to bring these numbers, if you were working on a scrap paper, bring these numbers back to the paper we were working on so we can create all of our different ratios. Okay, so for the ratio of our sides, we can do 15 to 25, and that reduces to 3 to 5. And for the ratio of our surface areas, I'm going to start over here on the left just to maximize my space, and that's 810 pi to 2,250 pi. So think of it again like reducing a fraction. We can get rid of these pi's. I can divide by 10, and I'm left with 81 to 225. And we can divide these one more time by 9. So 9 goes into 81 9 times, and 9 goes into 225 25 times. Okay, and then for the volumes, let's see, again, I'm going to start on the left. So I have 8,100 pi to 37,500 pi. And again, I can get rid of the 2 pi's. I can divide by 100, or basically get rid of those last 2 zeros. And so we're now left with 81 to 375. And those numbers are both divisible by 3. So 81 divided by 3 is 27. And 375 divided by 3 is 125. Okay, let's take our highlighter and highlight our important ratios here. So the lengths, we have 3 to 5. The areas is 9 to 25. And the volumes, we have 27 to 125. So let's see if we can make some observations here. So this time, none of them ended up being the same, right? We didn't have any that the ratios were the same as the ratios of the lengths. And the surface areas, looks like it's what's happening to it is just like what happened with the areas last time for the two-dimensional figures, that it's squared, right? If we take this 1 and 2 and square that, we get 1 and 4. And if we take the 3 and 5 and square that, we get 9 and 25. All right, so how about the ratio of the volumes? What is happening? It's not squared, it's not the same. Can you tell what is happening to the original ratio to get this volume ratio? Can you see what's happening to this 3 and 5 to get this ratio of 27 and 125? Hopefully you figured it out by now, but what's happening is those numbers are getting cubed. So the original ratio, if we take 1 and 2 and cube them, we get 1 and 8. And if we cube this ratio of 3 to 5, so 3 cubed is 27, and 5 cubed is 125. So if you know the original ratio, you can cube it to get the ratio of the volumes. Okay, so let's write down what we just found out. So if two similar solids have corresponding lengths, again, their height, width, height, slant height, radii, in the ratio of m to n, then their surface areas are going to be in the ratio of m squared to n squared. And if two similar solids have corresponding lengths in the ratio of m to n, then their volumes are in the ratio of m cubed to n cubed. All right, let's try some examples here. So if the heights of two similar triangular prisms have a ratio of 3 to 5, what is the ratio of their volumes? So we would cube that original ratio, so 3 cubed, we would get 27, and we would cube the 5, and we would get 125. Number 2, two cubes have volume in the ratio of 1 to 2. The length of one side of the smaller one is 8. Find the side length of the larger cube. So we know that their volumes are in the ratio of 1 to 2. We are going to work backwards and find the ratio of the sides. So we're going to take the cube root of these numbers. So we're going to take the cube root of 1, and that will be in the ratio with the cube root of 2. Well, I can take the cube root of 1. That's an easy one to figure out. That's just going to be 1. So I can reduce this to 1 to the cube root of 2. I can't simplify that one anymore. All right, now we know that the length of one side of the smaller one is 8. So I'm going to make this a proportion. I'm going to do 1 over the cube root of 2. And then on this side, the smaller one is 8, so that's going to go on top, and we're going to find the length of the side length of our larger one. Okay, so we're going to cross multiply here, and we get 8 times the cube root of 2 equals 1x, or just x, and that's it. So 8 times the cube root of 2 is the length of the side of our larger cube. All right, number 3. If two similar spheres have volumes in the ratio of 125 to 512, what is the ratio of their radii? So we know that their volumes are in the ratio of 125 to 512. So we take the cube root in order to find the ratio of their sides. Well, the cube root of 125, that's 5, and the cube root of 512, that's 8. So this is now the ratio of their sides, or the ratio of their radii. All right, number 4. If two similar cylinders have volumes in the ratio of 24 to 54, what is the ratio of their dimensions? So we take this 24 to 54, and we want to find the cube root of these numbers in order to find the ratio of their dimensions. And we can actually reduce this. If I divide each of these, let's see, by 2, we can get 12 to 27. I can divide again by 3, and I'm going to get 4 to 9. So we can use this as the ratio of the volumes. And we want to take the cube root of these numbers to get the ratio of their dimensions. I don't think I've said this before, but since this is just a ratio, it's okay to leave the radical in the bottom. We don't have to get rid of that because we're just dealing with a ratio. It's not saying that we're not giving an answer with a radical in the bottom. It's just a ratio. It's just saying how they're going to compare. All right, number 5. If the dimensions of a cube are tripled, what happens to the surface area? So basically what we're saying here is let's say one of the dimensions was x, then what would the dimension of the new cube would be? Well, if we triple it, it's now going to be 3x. Okay, so let's look at the surface area. We know that the ratio of the sides compared to, in order to get the ratio of the surface areas, I would square this. So this is the ratio of the sides, and I want to square it to get the ratio of the surface area. So now I would get x squared, and that would give me 3x squared. This is going to be the surface area ratio. Well, let's simplify this. It's going to give me x squared over 9x squared. And the x squareds can cancel out. So we're left with a ratio of 1 to 9. So the dimensions of the cube got tripled. They went from x to 3x. And then that means that the ratio of the surface areas basically got multiplied by 9. So it got 9 times as big. So the surface area is 9 times bigger than the original one. All right, if the dimensions of a cube are tripled, what happens to their volumes? So again, if we start with x and we triple it, and we're going to talk about the volumes now. So to get to the volumes, I'm going to take and cube this. So I'm going to have x cubed, and then we're going to take 3x and cube that. And when I simplify that, I get x cubed over 27x cubed. That's 3 cubed is 27. And again, I can cancel out the x cubes, so I'm left with 1 to 27. So if we triple the dimensions, we tripled them, the volumes end up getting 27 times bigger. So just try to imagine that. If you have a cube and it has, maybe the side length is just 1 on a cube, a 1 by 1 by 1 cube, then you take that and you have a bigger cube now that's 3 times as big, so that each length is 3 times as big. So it's a 3 inch by 3 inch by 3 inch cube. The volume of what you just created is 27 times more than what you started with. Where if you hadn't thought through this lesson, you may have just thought, well, the volume also gets multiplied by 3, and that's not true. So hopefully after this lesson, you feel smarter. And this is something that you can apply to real life for sure. If you think about building anything and you want to change the dimensions of what you were going to build, then the area, the surface area, the volume is going to get bigger, not just by the dimension. Like if you're going to double the length, well, now your area is not just double, it's 4 times as big because the ratio gets squared. Or the volume isn't just going to be twice as big, it's going to be that cubed. It's going to be 8 times as much. It's just a really good thing to understand and apply to real life situations.